We are going to talk about turbulence. I feel that when the definition of the subject is not clear, the discussion can become very turbulent. So we are going to ask the first question, like, what? What is turbulence? So the word turbulence has been used for a really long time to describe a phenomenon that is clearly not laminar. So we know laminar is smooth, orderly motions of flow with minimal mixing between different layers of the flow. So it's not the case. So when we talk about turbulence, the first impression comes to your mind. Like if you ask you, how would you describe turbulence, the characteristic turbulence with one word, what you could think about? Nonlinear, chaotic, irregular, unstable, multi-scale, ubiquitous, unpredictable. Well, if I can draw turbulence, I cannot show beautiful simulations. So, well, this is, I try to get this motivated, inspired by the Starry Night of Van Gogh's painting. It shows how the light, when it passes through the turbulent atmosphere, how it affects the images of stars and clouds we see by the turbulence in the atmosphere. And turbulence is really everywhere in our daily life, in your coffee, in tap water, in rivers, oceans, in atmosphere. We definitely feel turbulence a lot now, more frequently on plane. This is really a moment that turbulence makes me very nervous. So turbulence, it doesn't have a well accepted definition. It has an undefined definition. So there's no consensus that how we should define turbulence to fully capture all its complex physical properties. And it's mainly also because that we don't really understand turbulence. So turbulence is one of the greatest unsolved problem. We ask, why turbulence? And this is said that is also the question that Heisenberg would ask the God, why quantum mechanics and why turbulence? And he was pretty sure that God would answer the first question. I like the explanation on why turbulence given by Chandrasekhar in 1949 in one of his lectures. He said, consider a fluid as a mechanical system with a large number of degrees of freedom. Theoretically, it is capable of having a large number of different types of motions. Laminar motion is just one of the many possibilities. So just imagine if we can see the molecules in the air in this room, I ask you, what is the chance all these molecules move with the same velocity parallel to each other in a laminar manner? It is far more likely that the system, the nature, tries to present all possible motions simultaneously, and that will give the turbulent state of the medium. I figure out it's a bit difficult for you to see the molecules in the air, so I bring this demonstration with bubbles. And we can ask, probably you know the answer already, what is the chance for the bubbles that passively follow the motions of the air in this room to have move with the same velocity parallel to each other? So clearly it's not the case. Well, they drop on the floor, but you got but you got my point. So if you can, okay, so the initial separation of these bubbles is determined by the physical size of the bubble wand. But if you can track the separation of a pair of bubbles long enough before they disappear, it's not so successful demonstration, you would see that the separation between the bubbles increase with time. If they don't disappear, they would spread out and diffuse everywhere in every corner of the room. Just like what we see for chimney, they start from the smoke from a small radius of the chimney and very rapidly spread out and diffuse in space, in the turbulent atmosphere. Okay, so why we say turbulence is an unsolved problem? For a solved problem, we should be able to start some basic equations that describe the fundamental physical laws that govern the system. And by solving these equations, we would be able to predict precisely what happened at any given position, any given time of the fluid behavior. So let's start with the basic equations, which is known as the Navier-Stokes equations of fluid. So it's just a two conservation laws. The first is conservation of mass. At any point in space, there is no destruction, no creation of mass, so velocity is divergence free. The second equation is momentum equation. Tells, there's a question there?
Why should we expect to be able to do that? I mean, there's a lot of systems chaotic. I would sort of never hope to actually really be able to have arbitrary precision.
Yeah, exactly. That in most cases not our interest, and we'll go there later. But I want to start why people say it is an unsolved problem, not just in physics and also in mathematics. Okay, so second equation is a momentum equation. Is also Newton's second law describing, okay, so density. So this is just the acceleration and how the fluid moves under several force terms. So the first one is the pressure gradient force that drives the motion of the flow from high pressure to low pressure. For example, if you drink beverage from a box, we can press the bottom of the box a bit to increase the pressure at the bottom for the flow to move upward to our mouth. So this is this term. And the second term is a frictional term. So this is the viscosity. You see this is second order, so it's a diffusion term. It's a diffusion of momentum in viscous fluid. The friction comes from the collisions between molecules. This is also associated with energy dissipation. So the viscosity dissipates the turbulent energy in the system to heat. That increases the entropy of the system, so this is a reversible process, the energy dissipation. And there's also external force. For example, if I want to drive turbulence in my coffee, I stir the coffee by applying external force. So these two equations are very basic, but they become so difficult to solve in a turbulent state because the highly chaotic nature of turbulence, we know it means that if I change the physical condition, the initial condition or boundary condition a bit, it can give unpredictable, very large change of the outcome. So that we say the problem is not solved, but exactly as we know that in most cases we are not so much interested in predicting exactly what happened for an individual point in the fluid. We are interested in the statistical property of the entire system. And in fact, the fundamental property of turbulence is a statistical property. So there is a dimensionless physical parameter called Reynolds number can help us distinguish to tell the flow is in the laminar state or turbulent state. So we mentioned here the viscosity. Viscosity comes from the frictional collisions between molecules. So it is a measure how resistant a fluid is to motion, to flow. For example, we say honey is a highly viscous fluid. It's difficult to drive motion in honey, and the water has smaller viscosity. It's easy to drive turbulence there. So, okay, if I want to create some motion, for example, if I want to move this table, I need to apply some external force that drives the motion of the table. I also need to overcome the friction between the table and the floor. So if I want to drive turbulent motion in coffee, I apply some external force that drives the turbulent motion. I also need to overcome the frictional force between molecules inside the system. So if I compare this inertial force term and the frictional force term, the ratio between the two gave me this Reynolds number definition. So from the dimensional analysis, you can see that Reynolds number has expression as velocity of the flow, characteristic size of the flow. It can be the size of the cup, the size of the room, and kinematic viscosity. So if I have a large Reynolds number, it's easy to make the flow turbulent. If the Reynolds number is low, close to unity, we have laminar flow. Okay, so we know this from our daily life experience from tap water. If you increase the water velocity, increase the flux, Reynolds number increases, it's more easily to see turbulent flow in tap water. Another example, Reynolds number in the room, not just in the air, also in you, the crowd. Imagining if there are more hundreds of people coming into the room, mean free path decreases between individuals, viscosity decreases, Reynolds number increases. We can be in a very different situation as the dynamics of crowd can become from laminar to turbulent. So any irrational behavior of an individual, a push, could drive some local perturbations and can drive easily the turbulence in the crowd. In fact, that in very dense crowd, that is how the crowd crash happens because of the very large Reynolds number. So if you talk about astrophysical systems, we are dealing with very large size. Okay, not the size of the cup, size of the room. It can be the size of the entire galaxy. Then the Reynolds number can be very huge, much, much, much larger than unity. It can reach 10 to 10 orders of magnitude. So that's why we expect turbulence is ubiquitous in the universe, in astrophysical medium. Well, as I said, analytically, it is very difficult to solve the equations. So what we do is we solve these equations in our computers numerically to model turbulence. The problem is that with limited numerical resolution, we cannot really reach sufficiently small viscosity and realistically large Reynolds number. So imagine we model a galaxy in our computer. So instead of the galaxy is filled with gas, in our computer, the galaxy can be filled with honey, or milk chocolate, or even peanut butter because of very large numerical viscosity. So this is the situation we have for numerical modeling of realistic astrophysical turbulence in the universe. Okay, so not only we can look at the turbulence from the perspective of momentum, we can also look at from perspective of energy. So we know that, okay, there is a huge disparity between scales. So we know the energy is injected to the system at a scale comparable to the size of the system. The size of the cup, the size of the room, the size of the galaxy. This is a galaxy, a macroscopic scale where the energy is injected to drive turbulence. But the energy is dissipated through viscosity, the collisions between molecules, and that happens very slow process at microscopic molecular level. So this is because due to the collisions between molecules. And this happens on microscopic scales. So you cannot really make the huge gap between the scales, but you can imagine that there must be a huge gap between the macroscopic scale where the energy comes and the microscopic scales where the energy goes. So turbulence connects the very large to the very small. So then the question is, what happens to energy across all of these different length scales? Then we come to the energy cascade of turbulence. I like to use the analogy of water cascade. So now, okay, this is a water cascade. So the energy again comes from large scales where I drive the turbulent motions. And then the energy cascades, which means the energy is transferred across scales from large scales to smaller and smaller, smaller scales until at sufficiently small scale, by this term, the viscous dissipation becomes important, and that can transfer my energy, dissipate my energy to heat. And then it stops the energy cascade of turbulence and increase the entropy of the system. So if I plot the corresponding energy spectrum of turbulence corresponding to this cascade picture, so this is in wave number space, this is energy spectrum, which is defined as the turbulent kinetic energy per interval wave number. So large scales here, small wave number, where I input the turbulent energy. And here is the smallest scale corresponding to a large wave number where the energy is dissipated due to viscosity. And I have a power law distribution for the energy spectrum. Here is dissipated. Along this energy cascade, there is not much loss of the turbulent energy. So it has a constant energy flux across scales. So we have a question?
Sorry, very naive question. I mean, if the initial scales are sort of galactic, are some of the galaxies pretty flat, disk-like? And would it not then be like a 2D?
Yes, that's a very good question. Yeah, so usually when the observations, this is depends on the driving mechanism, the energy, the size of the energy injection can be different, but it's comparable to the thickness of the galactic disk, about hundreds parsec or kiloparsec. So, yeah, and when you're beyond that, the turbulence is like two-dimensional turbulence. Like the same thing happening in our atmosphere. We have the shell of the atmosphere where turbulence is 3D. Beyond that, it becomes more 2D-like. Okay, so so if I write this constant energy transfer rate, I have the turbulence energy, which is velocity squared, kinetic energy, but this corresponds to some length scale, and then divided by the time scale, which is the length scale divided by this velocity. And okay, I will write this way. So this ratio is a constant. I can immediately get the velocity is proportional to length scale 1/3 scaling. So velocity fluctuation drops towards smaller scales. And in terms of energy spectrum, I can get k to 5 minus 5/3, the famous Kolmogorov power law of turbulence coming from the energy cascade. So why I say there's not much energy loss along the energy cascade within this we call the initial range of turbulence. So we can compare these two rates, the energy transfer rate of turbulence and the energy dissipation rate by viscosity. So this one is given by the velocity divided by length scale is proportional to k to, let me find, okay, it's 2/3. And this one is the viscous dissipation is proportional to k squared. At large scales, the energy dissipation by viscous collision is very slow compared to the energy transfer by turbulence. So over all of these scales, the energy just transferred down to smaller scales without much energy dissipation. Until reaching the small scale, because this one has stronger dependence on k, it eventually across many, many scales can catch up with the turbulent energy transfer rate. And here it becomes important, it corresponding to where the dissipation happens to heat. So here is the driving wave number. So we see what turbulence tries to do. It tries to present all possible motions not on one scale, not on the driving scale, but across all different length scales. So the experiment that I showed earlier, you can see from the bubble separation that the turbulence has a multi-scale, it is a multi-scale phenomenon. The separation between the bubbles increases because the turbulent motions in the room has multiple scales. And another thing turbulence tries to do is it redistributes the energy I put to the system not on the single large scale where it happens, but across all different length scales for the purpose to maximize the viscous dissipation, to maximize the production of entropy through the viscous dissipation to heat. So as a result, we have a big disparity between the largest scale and the smallest scale. If I write the ratio between, so this is my energy driving scale and my energy dissipation scale, it purely depends on the Reynolds number as Reynolds number 3/4. Okay, so you see, given very large Reynolds number in astrophysical reality, the separation between the scale is huge. And we can also estimate the number of degrees of freedom. You can take the cube of that and get 9/4, a very large number of degree freedom, as we said earlier, and this was estimated by Landau Lifshitz. Okay, so the separation between bubbles is controlled by the length scale of turbulent motions. So if I write this L now as a separation between a pair of bubbles, I can get from this relation, so this R is just the L, the square, and then do some average. I find is proportional to time cubic. So if this separation grows linearly with time, we just call this normal diffusion, random walk in space. But now it has much stronger dependence on time as a cubic, which means the separation grows very fast with time. This, in fact, is called superdiffusion. It's already found, well, last century by Richardson, called Richardson dispersion or Richardson diffusion, describing all the passive particles in a turbulent background, the faster growth of their separation following these multi-scale turbulent motions from small separation initially to larger and larger separations, and they're very rapidly spread out in space following the superdiffusion scaling, and you can directly get it from the Kolmogorov energy spectrum of turbulence. Yeah.
Sorry, how does that work with causality?
Sorry?
How does that work with causality? I mean, you're assuming flat metric or?
Sorry, I didn't understand.
Assuming flat space-time or?
Yeah. Just the.
So then wouldn't it get too fast? What is I mean, the coefficient is small, or, I mean, it sounds like it's going to get outside of the light cone at some point.
No, I mean, this is everything, it will not continue beyond the driving scale turbulence. So it is the separation would increase, it's limited still by the turbulent volume of the medium. This is the largest separation is here, where you put the energy to perturb the motions of the fluid. Okay. And of course, if you talk about non-relativistic turbulence, its velocity is still quite small. Okay, so then we go to the third question. Why and where? Well, this is a relatively easy question to answer about turbulence everywhere. But it is difficult to realize it is everywhere. There's a saying that fish do not know they live in water. This demonstrates usually the most obvious, important, ubiquitous realities are often the hardest one to see and to talk about. For turbulence, not only we expect it theoretically it is everywhere in the universe because of the large Reynolds number of astrophysical systems, also observations by, so many years by different techniques measure the turbulence down to 50 meters. This is measured, for example, by Voyager, the spacecraft that recently enters the very local interstellar media, crossing the boundary between our local region of the heliosphere to the interstellar media of the galaxy, all the way in different astrophysical systems to tens of kiloparsec. And note that kiloparsec is about 10 to 19 meters. So this is about 10 to 20 orders of magnitude in length scales. So turbulence is measured everywhere across a huge range of length scales in the universe. So turbulence does fill the universe. So we do, no matter we realize or not, we do live in turbulence, and most astrophysical processes do happen in turbulence. Then the next question, another why. Why turbulence is important? And that is the main motivation for us to have the workshop to discuss Why we want to study turbulence? Why we care about turbulence? Well, we know that in daily life, turbulence factors into a lot of our technology in designing cars, airplanes, pipelines for transporting gas, and weather forecast. Although it's very difficult to make a long-term prediction because of the chaotic nature of the turbulence, it's difficult to predict, for example, the weather next week, how turbulent the flight is from Santa Barbara to New York. But it is still quite important for us to understand better the turbulence, and we apply our understanding from daily life phenomena about turbulence to studying turbulence in the universe. Let's again start from a very simple daily life example. So, okay, every day we make cream-based coffee, and if we purely rely on the diffusion of molecules to do the mixing, we know the typical diffusion coefficient in liquid is about 10 to minus 10, 10 to minus 9 meters squared per second. So if we apply this to the size of the cup, which is about 0.1 meter, so the time scale for us to how well mix the coffee with cream would be, so this is the size of the cup squared divided by diffusion coefficient. This will give the order of magnitude of several months to drink a well-mixed coffee if it's still drinkable. But what we do in reality is we drive turbulence by stirring the coffee, and that gave the turbulent diffusion coefficient about 10 to minus 2 meters squared per second, and we put a number here, we would get second as the time scale, and that is consistent with our daily life experience. We stir the coffee and we get it well mixed in a couple of seconds. Okay, now coming back to, so as I said, turbulence, because it presents all type of motions across different length scales and redistribute energy across different length scales, it can so much enhance the energy dissipation. I need to mention that although the energy dissipation happens because of the collisions between molecules, but the rate of this dissipation does not depend on viscosity. As you see, that it only depends on the energy transfer rate of turbulence, and that is already determined by the driving scale of turbulence and the velocity of turbulence at the driving scale. Similar story for turbulent mixing. Although the mixing is done because of the motion of molecules, but the rate of mixing when you apply turbulence only depends on the turbulent energy transfer rate, the turbulent motions in the medium. So turbulence very much enhance the energy dissipation, mixing, diffusion, and the transport of mass, momentum, heat in turbulent medium by manifesting the effect of a macroscopic processes for them to have the effect to be seen on large scales by accelerating the macroscopic process. Okay, so you know our human body contains many different elements. If you look at the lightest one, let's say hydrogen, it could originate from the Big Bang of the universe. So in that sense, we can say all of us have the similar age as the universe, 13.7 billion years. But most heavier elements in our body come from the production of stars, inside stars. So stars form from the interstellar medium, from the material in interstellar medium. And when stars get older, they also produce medium material and inject back to the interstellar medium. But both processes happen at slower rates compared to the turbulent mixing rate that makes the material produced from different stars. For example, if you look at in the interstellar medium of a volume about 200 parsec, it contains roughly the ashes and dust from stars about 100 million stars mixed together in this batch of interstellar medium. And some of them become the elements in our body. So we say we are made of dust from stars as a consequence of turbulent mixing in the interstellar medium. And in the universe, it's not possible to talk about turbulence alone, as turbulence has a best friend. that always accompanies turbulence everywhere in the universe. You know what is turbulence's best friend? Magnetic field, which is also ubiquitous in the universe. So the energy can flow both ways. The energy can flow from turbulence to magnetic field via a process called turbulent dynamo. That is a process that turbulence amplifies the magnetic field. So magnetic field could be very weak seed field in the early universe, and that is amplified by turbulence to account for the strong magnetic field we see today. Energy can also flow from magnetic field to turbulence through a process called magnetic reconnection. Okay, so now if we go back to, so because we have the inclusion of magnetic field, if we go back to the, can we go back? Oh, okay. Thanks. Okay, thank you. So if you go back to the basic equations that describe the flow of the turbulent motions, okay, now because we have additional force term coming from the magnetic Lorentz force, we need to add the J cross B, the Lorentz force term, govern the motion of fluid. J is the current density, B is magnetic field. We also need to add another equation governing the motion of a magnetic field because of the motion of the fluid. Okay, so we have the equation describing the time evolution of magnetic field. So we have this, the first term is the induction term, velocity cross B, how magnetic fields evolves under the effect of fluid motion. And we also have a similar diffusion term. Okay, so this is a diffusion in momentum. This is a diffusion in magnetic field. It's also associated with dissipation of magnetic energy. So in a system, we have a lot of energy stored in magnetic field. Through this, the energy dissipated through the diffusion of magnetic field. If we also compare the ratio between the two, these two terms, we can get a magnetic Reynolds number similar to the Reynolds number in hydrodynamic turbulence. So we have it as UL here. It is not viscosity, but diffusivity of magnetic field. Again, because of the large disparity of where I inject my energy on large scales and where the energy dissipated by macroscopic diffusion magnetic field, there's a huge disparity between the two, and it gives the magnetic Reynolds number also much larger than 1. This one can reach 10 to 20 orders of magnitude in astrophysical medium. Okay, so now with magnetic field, one may think the story should be different about turbulence. Because of the magnetic tension force, so it must be very difficult for turbulence to drive any motion. So whether I should just have the wave-like oscillation of magnetic field, because whenever I try to make some perturbation of the magnetic field line, the tension force would try to bring the magnetic field to the equilibrium. Is this the case? I would say the biggest discovery in the field in MHD turbulence, when there is a magnetic field getting involved with turbulence, is finding this is not the case. So instead of wave-like oscillations around a fixed space in space, it is found that from the paper starting in 1995, Goldwasser in 1995, and then Lazar and Vishnak 1999, and many other studies after that, the strong interactions of these wave-like motions is so strong that it can make the wave-like oscillations decorrelate, lose its memory within one wave period. So if I okay, so instead of a coherent wave-like oscillations, the magnetic field does have the freedom to move around, to be moved around by the turbulent motions. So if you do the numerical experiment, you don't see the wave-like propagation of magnetic field for many wave period, but you still see the turbulent motions which I draw here in the direction perpendicular to magnetic field. That magnetic field is still freely moved around and have a mixed feature like similar to turbulent motions in hydrodynamics case. And if you measure a pair of magnetic field, the separation between a pair of magnetic fields, and you can see the similar Richardson scaling. Okay, here. If you measure a pair of magnetic field lines, the growth of the separation between field lines, they still grow similar to the passive particles in turbulent flow. So not much changed. This is a very important finding, as we don't need to forget everything we learned without magnetic field. So many things here still hold true in the presence of magnetic field. For example, turbulence is still very important in accelerating the energy dissipation. In addition to the energy dissipation from by viscosity, now there is additional energy dissipation by diffusion of magnetic field, with this one enhanced a lot by turbulent motions. And this is very important for us to understand some astrophysical puzzles. For example, we know our sun has a corona. So now, okay, here I'm drawing is the sun, and it has, I'm trying to draw the corona of the sun. Okay. So, okay, the corona is the outermost layer of the atmosphere of the sun. It is far from the core. But it's found that the temperature of the corona is much higher than the inner layer of the atmosphere, closer to the sun. Thousands times of higher temperature in the outer layer. So for several decades, scientists have been searching for what is additional source for this heating to explain this high temperature. We know the sun produces strong magnetic field itself. So its surface is covered by the strong magnetic fields like a blanket. So one likely, most promising candidate for explaining this is that the energy can come from the magnetic field to dissipate to heat to explain the high temperature. But the key here, how efficient it is. If this heating through the dissipation of magnetic field happens at the microscopic level, it is too slow to have any visible significant effect on macroscopic scales for us to see. So turbulence here plays a very important role in accelerate this through this process here for the effect to be significant, explain observations. And this could be also the physical picture behind many powerful explosions, bursts in our universe where the magnetic field is very strong, a lot of energy is stored in magnetic field. The question is really how we can release this energy to produce energetic particles and energetic photons efficiently. So turbulence can play a very important role to help this energy release from magnetic field. Yeah.
The equations you wrote was for incompressible fluids so far.
Yes. Yeah.
Is that a valid approximation in astrophysics context?
I mean, depends on the medium compressibility of the gas. So we can also deal with highly compressible case when the temperature is low. So in this case, there are some extra terms added for the density change of the medium. But the thing is, usually it's found that in at least a non-realistic region, the coupling between the incompressible and compressible components of turbulence is weak. So we can still, everything talking about here, the dynamics of magnetic field and turbulence still holds true even when the medium is compressible. And also, we also find the dynamics of magnetic field, even in compressible medium, still dominated by the incompressible finite component of turbulence. So we need additional things to describe the compressible component, but everything here for incompressible and the dynamics of magnetic field is still true.
And how robust is the Kolmogorov spectrum in this more general case when you have compressible?
So this is for velocity kinetic energy spectrum. Depends on the energy fraction in different components. In most of the cases, we still find the solenoidal incompressible motions dominate the dynamics. So if you have the spectrum of the all system, you still have the Kolmogorov. But if you want to look at the compressible component, then the velocity can be steeper because the dissipation can happen through shocks, and the density can become shallower because it creates a lot of density clumps in the medium. You do have some decoupling between the density distribution and the velocity and the magnetic field distribution. But this Kolmogorov power law somehow is measured through these different length scales, including Voyager measurements and some measurements in the galaxies and galaxy clusters, roughly consistent with the Kolmogorov power law of turbulence. So another puzzle is one of the four messengers from the universe is energetic particle. We call them cosmic rays. So every moment we are under the shower of cosmic rays. At the sea level, the rate for a cosmic ray particle pass through my body is about once per second. So when we look at these energetic particles from the universe, and we see them come from all possible directions, isotropically, there's no preferred direction indicating where they come from the universe. So the origin of cosmic rays has been a century-old puzzle. Last century, there was a model proposing that these particles must be generated from the early universe everywhere in space. That's why we see them come to us from all directions. Until more recently, we know that these particles are generated from powerful factories in the universe. We call them accelerators. And by the way, these accelerators usually have very strong magnetic field to confine high-energy particles. And these magnetic fields can be amplified by turbulence. And the strong magnetic field is necessary for the particle to be accelerated until they reach the speed close to the light speed. Although they move with light speed, they do not travel directly from their accelerator to us along a straight path because these are charged particles. So they interact with the turbulent magnetic fields that fill everywhere in the universe and get scattered. And the scattering changes their moving direction so much that they lose the memory of where they come from. So when they reach us to Earth, we see them, they come from all directions as if they were produced everywhere. So this is another example to show how turbulence and their interaction with magnetic fields affects our observation. So, okay, so we see that turbulence connects the very large to very small, and this is very important in astronomy as it connects, yeah.
Does this scattering happen in the intergalactic medium, or it's sort of near the origin? Where in the trajectory of the particle does it happen?
It also happens in the intergalactic medium, yeah. I mean, yeah, it depends on the relation between the gyroid, the energy of the particle, and the structure of the magnetic field, how strong they can be, the interaction is. Yeah, so turbulence connects the very large to very small. This is so important in astronomy because our telescopes can show us something that we can see on large scales. So this connects what we can see on large scales to what we cannot see on microscopic scales, these very important astrophysical processes. And turbulence connects, of course, our daily life and the universe, and connects diverse astrophysical phenomena. So there are many, many other examples I don't have time to discuss, showing the importance of turbulence in astronomy as already foreseen by Chandrasekhar in 1949. And it's also the purpose that we come here together to share our new insight of turbulence that can bring to existing long-standing astrophysical problems and also frontiers of astronomy. Although we still don't fully understand what is turbulence, we cannot even reach agreement on how to define turbulence, we already so much benefit deeply and broadly from our understanding of turbulence, our understanding of universe from different perspectives. Okay, so I will stop here and thank you very much.
Yeah, I have two questions. One, going back to your earlier answer that in galactic disks, the flow is two-dimensional process. That has a different cascade, has a Kreisman's cascade because of the extra conserved quantity. Is it actually observed in astrophysical scenarios?
Yeah, that is a good question. I mean, there's an inverse cascade for 2D turbulence, and I think depends on the observer's view. It is edge-on or face-on galaxy. And we do see the change of the slope when we can, from the transition from 2D to 3D, the change of the spectrum when we measure, for example, the structure function of turbulence in the galaxies.
My second question was, are there examples where relativistic effects are important? Because relativistic fluids are not compressible in general.
You mean relativistic, yeah.
Relativistic hydrodynamics in some,
Yeah, so there are studies, both analytical and numerical studies, studying turbulence, MHD turbulence in relativistic regime. And it's found that the aphanic turbulence stays very much similar to the non-relativistic regime, but the coupling between the incompressible and compressible components can be quite strong in relativistic regime. So that can affect like the fast and slow modes when we deal with them in relativistic case. Yeah.
So we're using Reynolds number to argue for presence of the turbulence in our galaxy, Reynolds number being large. But on the other hand, if I will take, say, cosmological flows at early stage, the potential flows, there's no turbulence, they probably have huge Reynolds number because there's no viscosity practically. Does it mean that the Reynolds number is actually not sufficient criterion to know whether you have turbulence or not?
I think I would agree on that because this gives us a rough estimate based on the dimensional analysis. I guess it very much depends on where the energy is injected. It's not necessarily the size of the system. Right? It also depends on the mechanism that we put the energy into the system.
But it also depends on the fact that these nonlinear terms are actually important.
Oh, you are talking, okay.
And if you don't have nonlinear terms, then kind of standard derivation of Reynolds number also falls off.
Yeah, you cannot deal, I mean, this term is small, but it's not zero. So, yeah,
Exactly.
yeah, so it can be exactly zero.
I actually have a feeling that when Reynolds number is very huge, it primarily means that it is irrelevant, rather than that you have a turbulence.
Yeah, it could be in the very extreme case, yeah, it's a different physics there.
Do higher point velocity correlators play a role in astrophysics or any other application of turbulence?
Higher order?
Higher points correlator, more than 2 points. 3 points.
Yeah. So the 2-point structure function is directly related to the spectrum here, but you can also do the multiple point statistics to get more information from turbulence. Yeah, so there are tools for analysis on that.
But do we, I mean, what do we know about higher points?
So this is the simplest, the first order statistics that tells how the energy spectrum is, give you the average sense, like take the medium. But if you're dealing with, let's say, for example, highly homogeneous case, that you cannot really see the information, all the information just by measuring this energy spectrum or 2-point statistics. You probably need to get more complicated statistics to get more information. Now the average, the statistics by more detailed distribution in space.
question about turbulence.
Uh-huh.
You asked, what would be most helpful to understand? For example, statistics of large events, or statistics of typical events, as in how much energy flux, like, which is sort of everywhere, but we don't know what it is.
Yeah, I guess more recently I'm interested in this intermittency in turbulence. So when we take a flight, more frequently we have some small minor bumps, but occasionally we may have a really disaster with a very large perturbation in turbulence. So I guess I care about that the energy transfer here, which I plot, is usually believe it dominates the energy channel through the system. So comparing to the frequent, weaker events and more rare but strong events, which is more important in terms of not just the energy transport, but also for the particle acceleration in the case with magnetic field, how the energy is released and how the energy is converted to particles, which is a dominant channel. Yeah.
So you mentioned this energy injection a couple of times. What's the dominant mechanism?
Oh, yeah. So it really depends on the astrophysical system of interest. For example, in the heliosphere, we believe the activity of our sun plays a very important role in driving the turbulent motion. And in our galaxy, we believe that the explosions of stars, massive stars, at the end of their life put a lot of energy in our galaxy, can drive the turbulent motions. And on larger scales, we think the collisions between the mergers of galactic clusters and galaxies can drive turbulence on even larger scales and give more dynamical picture depending on the size and the environment we consider. Yeah. And I just mentioned that, so these are large scale, then turbulence may also be driven by smaller scales, by instabilities, and the reconnection of magnetic field can also drive turbulence. So when the Reynolds number is large, it's just very easy to drive turbulence, whatever mechanism you have. Yeah.
Just wondering if there are systems where you might have a quantum analog of turbulence, in the sense that when you describe it in terms of momentum flow, that it seems completely irrelevant, but when you describe it in terms of the energy cascade, one might wonder whether there could be analogs in quantum mechanical systems and what that would look like. In a similar way to trying to characterize quantum chaos as opposed to classical chaos. Has work been done on that?
Yeah, I mean, I know there are some studies on like vorticity, vortex in quantum fluid, and it's quite different system. There could be some common tools to analyze that, but I think it is still, I mean, there is some connection, but it's not so clear like how much we can apply what we learn here to quantum system yet.